Hello, today we're going to be talking about systems of linear equations given to variables. The first thing that we're going to talk about is exactly what that means. If we have a system of linear equations, it means that we have a group of linear equations, of two or more linear equations that are considered together. So if we have 2x plus 3y equals 4, that's one linear equation, and 3x minus 2y equals -7, that's another. But if we consider them together, this is now a system of linear equations. A system of linear equations will have either no, one, or infinite solutions, if we're talking about linear equations specifically. And we can see this by drawing them out, because a linear equation is going to be one that is just a line on the graph, right? Hence the name. So let's say we have these three charts. If we have one solution, it's going to be two linear equations that cross at one point somewhere. That's your one solution. That is also known as an independent system. You can have infinite solutions if the equations are basically the exact same equation. They can be stated differently, but if all the points are the same, then we wind up with infinite solutions. This is called a dependent system of equations. You can also have zero solutions. Why is there zero solutions? Because these two will never cross at any point in time. They're parallel. They'll just run infinitely that way and infinitely this way without ever crossing, so they have zero solutions. This is called an inconsistent system of equations because these two are inconsistent with each other. They will never have the same values. But so if we take this, let's figure out what kind this is without graphing it. We can do that one of two ways. We can, let's see, do what's called the substitution method, where we find the value of one variable in terms of another in one of these equations, and then substitute that value into the other equation. In order to do that, again, this is called the substitution method, which by its name, you might guess that we're going to use substitution. We can grab either of these. Let's just choose this one. So we get 2x plus 3y equals 4. And let's pick one of these variables to get in terms of the other. Let's do x. Normally we'd do y, but I see a 4 and a 2 there, so we have some easier math if we divide by 2 than if we divide by 3. So first we're going to get everything over to the other side and keep the x on this side. So we have 2x equals 4 minus 3y. So now we can divide both sides by 2 to get x completely on its own. 2x divided by 2 is x. 4 divided by 2 is 2. And negative 3y divided by 2 is negative 3y divided by 2. Which can also be written as negative 3 over 2y. So we have this now, which we can substitute in to the other guy. Let's take 3x minus 2y equals -7 and substitute in what we know for x, this guy right here, and solve from there. So we'll have 3 times the quantity 2 minus 3 over 2y minus 2y equals -7. 3 times 2 is 6. 3 times 3 halves is -9 halves. Sorry, 3 times -3 halves is -9 halves. And then we bring down our negative 2y and our negative 7. Let's bring our 6 over here. By subtracting it from both sides, we get negative 13. And let's get these in like terms. We have negative 9 over 2y minus 4 over 2y, right? Because if we have 4 over 2, 4 divided by 2, we get 2. Because 2 times 2 is 4, right? So if we add these now like terms together, we get negative 13 over 2y equals negative 13. Now, in order to get y on its own, we'll divide by negative 13 over 2, which is the same as multiplying by negative 2 over 13, isn't it? Because if we have negative 13 over 2, when we multiply it by negative 2 over 13, number one, this is going to cancel out, because negative times negative is a positive. This is going to cancel out, because 2 over 2 is 1. And 13 and 13, same thing, so we get 1. We're also going to multiply this guy, negative 13, by negative 13 over, or negative 2 over 13. So if we have negative 13 multiplied by negative 2 over 13, again, we can cross this out because this is 13 over 1. 13, 13, this is going to cross out. We get a positive 2. So we know that y equals 2. But what is our x? Well, if we plugged this value for x in here, we can plug this back in here. So, forgive me, I'm going to go a little out of order here, and I'm going to go up here. If we have x equals 2 minus 3 over 2y, but we know that y equals 2, we know that x equals 2 minus 3 over 2 times 2. X equals, multiply 3/2 by 2, we get negative 3, so 2 minus 3, sorry, that is a 3. So 2 minus 3, negative 1, right? X equals negative 1. So, we know that the system for this solution of equations, the point at which they intersect, occurs where x equals negative 1 and y equals 2. So x equals negative 1, y equals 2. This is our solution for this system of equations. And that's how to do it by the substitution method. There's another method to do it with. There's another method that you can use. And we're going to erase all this and go back to our original equation. 2x plus 3y equals 4, or rather our original system of equations. And 3x minus 2y equals negative 7. This is our original system of equations, right? We figured out by substitution that the solution is negative 1, 2. The point at which these two intersect is negative 1, 2. Another way you can check that out, real quick before we move on to the other way, is to plug this back in. If we have 2 times negative 1, right, because x is negative 1, plus 3 times y, which is 2, equals 4. So we're substituting the x and y values back into this function and then seeing what happens. Negative 2 plus 6 equals 4. Isn't that right? 6 minus 2 equals 4? All right, so that one checks out. Let's try this one. 3 times x, which is negative 1, minus 2y, which is 2, equals negative 7. Negative 3 minus 4 equals negative 7. That's true as well, right? So it works out. We've proven that these were correct, which is valuable in other ways, in other function types, but I'm just showing you that it was in fact the answer that we were going for. Now we're going to use, instead of the substitution method, which we've already done, we're going to use what was it? The elimination method. So the elimination method is where we're going to get rid of one of these variables by subtracting one of these equations from the other. So we can't do that right away, right? Because if we subtract 3x from 2x, we get negative x. And if we subtract negative 2y from 3y, we're actually adding 2y. That would be 5y. Well, we'd wind up with something that wasn't what we wanted. We'd wind up with just another equation. So what we're going to do is we're going to pick either x or y, and we're going to get them in the same term. So for my purposes, I'm going to pick x, and I'm going to make these equal. How am I going to make them equal? Well, I'm going to multiply this equation by something and this equation by something such that these two wind up being the same. So if I wanted to get 2x and 3x to be the same, I would multiply 2x by 3 and 3x by 2, and I get 6x in both of them. But in order to not change the equations, I need to multiply all of it by that value, right? Because if I'm multiplying both sides, I'm not changing the value. So if I need to multiply this one by 3, it would be 6x plus 9y equals 12, right? Because 2x times 3 is 6x, 3y times 3 is 9y, and 4 times 3 is 12. Well, this guy needs to be multiplied by 2, so we can get a 6x here. 3x by 2 is 6x. Negative 2y by 2 is negative 4y. And negative 7 by 2 is negative 14. All right, so we've seen this in long division before. We will go ahead and subtract one of these from the other. We're just going to flip all the signs and add them together to make it easier. Boop, boop, boop. So 6x minus 6x, we know that that's 0, right? 9y plus 4y, that's 13y. 12 plus 14, that's 26. We have 13y equals 26, right? Because we can just throw that out. If we divide both sides by 13, we get y equals 2. Right? So we're on the right track so far. From here, we just plug in our y to one of these functions and solve for x. Same as we did on the other one. So we're just going to pick this guy real quick to get this done and over. 2x plus 3 times 2 equals 4, because we're substituting in 2 for the y value, because we know that y equals 2. So 2x plus 6, because 3 times 2 is 6, equals 4. 2x, we want to get it on its own, so we subtract 6 from both sides. We get 2x equals negative 2. Now we need to get rid of this 2. We divide both sides by 2, and we get x equals negative 1. Look at that. It's exactly what we wanted. So there's two ways that you can solve this. You can solve it using substitution, which is where you get one of these equations in terms of one of their variables and then substitute around until you get everything that you need. And there's elimination, which in my opinion is a little simpler because you can figure out how to get rid of one of the variables right quick and get a single variable equation that's easy to solve, and then you just plug it back in. So that's if the equation has one solution. We're going to modify this a little, and we're going to talk about what it would look like if there was 0 solutions. We're going to modify this just a bit. If we have 2x plus 3y equals 5, coupled with our 2x plus 3y equals 4. So let's go ahead and do substitution on this, right? We're going to solve this one in terms of x. So we have 2x plus 3y equals 4, nothing we haven't seen before. We get 2x equals 4 minus 3y. and we divide all of it by 2. X equals 2 minus 3/2 y. So now we're going to take this and substitute it back into the other one. So we have 2x plus 3y equals 5, and we know that x equals 2 minus 3/2 y. So 2 times 2 minus 3 over 2y plus 3y equals 5. Distribute the 2 here, we get 4 minus 3y plus 3y equals 5. Now hold up. We have a negative 3y and a positive 3y. What's any term added to the negative of its term? 0. So this just goes away. And we're left with 4 equals 5. When is 4 going to equal 5? Never. That's not a thing that happens. So this is a system of equations where there is no solution, or where they go next to each other or parallel to each other on the graph forever. They're never going to cross. This is our inconsistent system of equations. So that's what it looks like when you get to an inconsistent system of equations. You get something that's impossible. We're going to modify this again, and we're going to talk about what happens when you get an infinite number of solutions. We're going to go 4x plus 6y equals 8. Now you might have noticed this is just this with all the terms multiplied by 2. If you catch that when you're looking at something, that one is just the same but it's multiplied by some variable or some value, then you know that they're equivalent. You know that they're going to literally be the same. Every single point on them is going to be shared. Now that's if you can eyeball that. But what happens if you try to solve and you wind up, where do you wind up? So let's do this again, right? We have our 2x plus 3y equals 4. We're going to memorize this one by the end of this. 2x equals 4 minus 3y. X equals 2 minus 3/2 y. Now we're going to substitute this x into this guy. 4x plus 6y equals 8. Our x is 2 minus 3/2 y. 4 times 2 minus 3/2 y plus 6y equals 8. 4 times 2 is 8. 4 times negative 3/2 is negative 6, because we're going to have 4 divided by 2, which is 2 times 3, which is 6. Y plus 6y equals 8. Again, hold up, what do we have? We have negative 6y and positive 6y. This disappears. It becomes 0. And we're left with 8 equals 8. And we're going to ask ourselves the same question that we asked ourselves when we had 0 solutions. That is, when is this going to be true? Answer, always. 8 is always going to equal 8. You can't make it not equal 8 unless you literally change the value of the equation. So, these two equations line up right over each other. So they're said to be a dependent system with infinite solutions. And that's what that looks like if we wind up with something that's always going to be true. So to recap, you can use the substitution method to solve. The substitution method is where you substitute in, you solve one equation in terms, not turns, it's not a bird, of one of its variables. You substitute that in to the other equation. You solve and you pop the value that you get, whether it's x or y, into the other equation. We saw a demonstration of that. We know how that works. These are just notes if you want to take them real quick. And there they go. We know substitution. We know elimination. We get one of the variables in both of the equations to be equivalent. The same value, so that when we subtract one from the other, we get 0, and it disappears. It gets eliminated. Then we do the same thing as we do with substitution. We plug that value into really either of them, but yeah, either equation. And solve for the other. Variable. So there's elimination. There's notes on it. Go ahead and take them for yourself real quick. And there they go. So we've done substitution. We've done elimination. And we know when there's one solution to the system of equations, they're going to cross at exactly one point. That's just that simple. But we know that this is called an independent system of equations. We know if it has 0 solutions, they're never going to touch. There's never going to intersect, which means that they're an inconsistent system of equations. And if they have infinite solutions, that means they're the same equation, effectively, and they're dependent. They are dependent on one another. And there you have it. That is how to solve a system of linear equations given two variables. Thanks for watching. If you have any questions, please leave them in the comments below, and I will do my best to respond to them.